Good afternoon, everyone. My name is Giulia Pelliccia. Today I'm going to present part of my PhD research titled 4D Vertical Printing, Hygro-Responsive Shape Change Deformations with Complex Non-Planar Rested Geometries. I'm part of the group, the research group of the Department of Civil and Environmental Engineering at University of Perugia in Italy, led by Professor Fabio Bianconi. This research is about the investigation on many configurations, material architecture, and 4D printing methodologies that can help in the development of hygro-responsive wood-based actuators that can possibly be used in architecture as airflow controllers. Wood is a natural smart material whose hygroscopic properties are direction dependent. Such behavior can be seen in nature, looking at the pine cone scales bending, for example, which has been studied by several authors. And such bending mechanism is due to, among many other factors, the fact that these scales are composed of two different tissues which have different hygroscopic coefficients. Such behavior has been replicated by several authors to fabricate wood laminates, which are composed of two different wood veneers with a cross-grained configuration. And these two layers have different hygroscopic coefficients and different thicknesses. The same principles have been then extended to 4D printed wood polymer composites. So different levels of kinematic actuation have been, excuse me, I think someone has a microphone. Different levels of kinematic actuation can be achieved by managing the printing properties and the geometric patterns and the overall design of the material architecture. In the research I'm going to present today, we have used the Prusa i3 MK3 Plus printer with a laywood filament as expansion layer and PLA filament as constraint layer. So the standard methodology to print such hygro-responsive actuator is based on initially flat print on the printing bed that, after the exposure to humidity, reaches complex deformation. However, programming such complex deformation and in particular programming double curvatures can be challenging if we start from almost bidimensional initial geometry. This is why we propose in this research a different methodology to print such 4D printed hygro-responsive actuator, which also takes into consideration a vertical expansion of the laywood filament. As we know, in 3D printing, the wood fiber inside the laywood filament are oriented along the toolpath direction, and the hygro expansion occurs in the orthogonal direction to this toolpath direction. In standard 4D printing methodology, we used to consider such orthogonal hygro expansion in the XY plane. However, we can still consider the printed filament in its three-dimensional shape and consider that it also has a vertical component of hygro expansion. So through this 4D Z printed methodology, we aim to design hygro-responsive actuators which are non-planar in their rest state geometries. Significant application of such methodology can be found in the replication, reinterpretation of the Lilium-Casablanca bending mechanism, which has been already studied in previous research, in particular by Simon Schleicher and David Correa. Many authors have investigated plant motion principles to transfer them to architecture. In particular, Schleicher in his research have focused on the bending motion of the lily tepals, explaining that this motion happens thanks to a differential growth rate between the edges and the central midrib. He also focused on the relationship between different radii of curvature that are used to model the shape of the tepals and the overall curvature of the tepals. Based on such work, Correa also reinterpreted in a previous research such lily deformation through a 4D printed actuator made of laywood, ABS, and TPU. In his methodology, he printed the 3 tepals singularly on the printing bed, and successively he assembled them together and curved them manually thanks to a central part made of TPU, which is very flexible and allows the tepal to bend and have a configuration similar to the closed tepal in the real lily. The proposed 4D printing methodology is intended to overcome this successive manipulation of the printed geometry by printing an already curved shape in its rest state. This workflow is divided in 2 main steps. In the first step, we print the laywood body of the actuator in a single piece in the Z direction. This results in an empty shell with very thin walls and 0% infill, no bottom layer and no top layers. Then we need to print a PLA support in order to lay down the laywood body horizontally on the print bed over these supports to print the PLA constraint layer directly on the surface of the laywood body. The direction of the PLA constraint raster pattern follows the direction of vertical expansion of the laywood filaments, so that the PLA can constrain this deformation. And last, a laywood bonding layer is overprinted to ensure a good adhesion between the 2 materials. Following Schleicher research regarding the influence of the various radii of curvature in the final curvature of the tepal, a dedicated grasshopper algorithm was developed using Galapagos evolutionary solver to optimize the shape, the geometry of the actuator, and make sure that such shapes are effectively printable through our tools, through our printer. So in this optimization algorithm, we have 2 steps. In the first steps, we define the design parameters as variable, which are the 3 radii of curvature, the height of the overall height of the actuator, and positioning and inclination of the laywood body on the printing, inside the printing volume, which I'm going to discuss better in the further slide. The second step involves instead conditions for printing. So we basically check whether the the geometries are printable or not by adding first a limitation of the maximum curvature difference between the minimum and maximum curvature on the surface, and second, automatically excluding those geometries that intersect the printing volume. So this is a more visual way to explain such algorithm. So basically, by defining the radii and heights, we have many solutions calculated by the algorithm. After choosing one or more optimized solution, we can print them using Laywood. Then the last step concerns the positioning on the printing bed. This is crucial since we are working with a 3 degree of freedom printer. So collisions can easily occur between the extruder block and the Laywood body laying on the supports. So to avoid such collisions, first we need to set such limitation on the maximum curvature allowed on the surface. Second, we need to calculate the inclination of the Laywood body on the supports to ensure that the extruder block doesn't collide with it. And the algorithm calculated an angle of 5.5 degrees for this specific geometry. In this diagram, we have a comparison of the structure of the various tepals in the lily, in the previous 4D printed lily by Correa, and in the proposed 4D Z printed lily. The previous 4D printed lily is basically a direct result of the translation of the biomimetic principles from the lily to the 4D printed actuator. In particular, we see that the bilayer expansion is located along the edges, and the curved shape of the tepal needs to be reached manually after printing. Instead, in the 4DZ printed actuator, we have the bilayer expansion in the central area, and basically the bending deformation of the tepals happens just thanks to the geometry itself, and no other intervention are needed on the actuator after printing. Also, the actuator is already printed in a unique piece, so there's no need to assemble the parts. So among the many optimized solutions from the algorithm, 2 were selected, called Lily A, which has higher difference of curvature between the 3 radii, and Lily B, which has less curvature change. And in order to assess the performance of such actuators, we used Kinovia and other image analysis techniques, but Kinovia is software which has already been validated by other research for tracking the motion of Hygro-Responsive actuators. And we observed that Lily A, which has Lily B, which has less curvature change, achieved higher curvature, and also reached the hygroscopic equilibrium faster than the other. Last, we also observed that the 4DZ printed achieved the equilibrium faster than the 4D printed one, taking 180 minutes compared to 300 minutes. In conclusion, the development of such 4DZ printing methodology allows to take advantage of the different components of the hydro-expansion of wood-based filaments. And this was successful in the replication of the Lilium Casablanca structure, allowing to produce a unique piece actuator, which doesn't need any other intervention after printing. Moreover, such actuator resulted in a more responsive and quicker hygro-responsive deformation. In future research, such methodology could be applied or proposed with other materials for 4D printing. For example, materials with can have higher responsivity or can have less delamination issues. Moreover, they can be studied for scaled up solutions, and their application as airflow control, passive airflow controllers in indoor environments could be also investigated. Thank you for your attention.